Hello and welcome to video number 2 for chapter 12, comparing independent means. So let's pick up where we left off, talk about hypothesis test. Remember we just went over comparing the different confidence interval formulas for single paired independent tests. Now we're going to move to hypothesis testing, where once again our null hypothesis is going to state no difference or nothing, so our mu1 is going to equal mu2 against an alternative hypothesis, in which case if it doesn't equal to two-sided test, if mu1 is greater than or less than, it could be either a right-sided or left-sided test. We'll be figuring out our t-statistic, our t-stat, for our x bar 1 over x bar 2, or x bar 1 minus x bar 2 over the standard error of the difference between our x bar 1 minus x bar 2, where our standard error is calculated by the square root of the variance squared of group 1 over n1 plus the variance squared of group 2 over n2. Remember, you can calculate degrees of freedom Welch or degrees of freedom conservative, in which case we always side with degrees of freedom conservative because we will not be calculating the Welch degrees of freedom. After we state our hypothesis, do our test statistic, we can figure out our p-value. So we'll convert our t-stat to a p-value with a table or software, and D will determine the significance level. We'll compare our p-value to our alpha level. So moving to a hypothesis test, we state our hypothesis of mu1 equals mu2 versus an alternative hypothesis where mu1 does not equal mu2, so it's going to be a two-sided test. In prior analysis, we calculate our sample mean difference of 34.75 milligrams and a standard error of 13.563 with our degrees of freedom conservative equal 19. So when we plug all this in to get our t-stat, you'll get 34.75 divided by 13.563 equals 2.56 with degrees of freedom 19. So we go ahead and look up degrees of freedom 19 in the back at this will be at 0.95 or 0.975 cumulative probability to the right because we're doing two-side sample, and we see what our critical cutoff point is to determine if we have sufficient evidence against the null hypothesis, in which case we get a p-value of 0.019. So it's good evidence against the null hypothesis. So this evidence against the null hypothesis is significant at alpha level of 0.02 or greater, but not at a 0.01. I'm going to bring over the, if I can bring it over. I guess I can't bring it over right now. Interesting. I was going to bring over an Excel sheet. There we go. That I told you I would have. So in this Excel sheet we have our type A personalities and type B personalities and their cholesterols associated with them. I'm going to show you how you calculate this in Excel. So if you go to your data tab in Excel and you might have a data analysis tab here. If you don't, you just have to go to your add-ons and add in the package for a data analysis tab. There's a couple different ways to do it for Macs. I would just Google search it. I will have a video up later that goes over this data analysis when we do our data set 3. But all you have to do for this data analysis to get that t-value, just to show you, just go to data analysis. For this one we're going to be doing a t-test of paired two sample means. You hit OK. We hit our variable range 1, which is already selected, and our variable for range 2, which is also selected here. And then you would put in your output range, so you determine where you want to go. H3 is fine, and then you just hit OK. And here you go. Here's your t-test paired two sample for means. As you can see, it calculates your degrees of freedom, your t-stat 2.56, which is what we had in our PowerPoint. It gives you your one-tail and two-tail test. So remember, we were doing a two-tail test, and we got a p-value of 0.019, which is exactly how you can calculate this. So this is how you can do a group of data analysis for t-statistic using Excel. Heading back to our PowerPoint. So now we're going to move, where did we leave off? We did hypothesis testing, we did the example, and then here's how the SPSS outlook. So this is what it would pop out in SPSS if you did it, where SPSS does have a little bit better software where it actually calculates the equal variances assumed and equal variances not assumed for each of these, which is what we're going to get into right now. So when we get into equal variance T procedures, this is kind of optional, and what this is eventually going to get us to, leading into is advanced ANOVA techniques. It's also called pooled variance T procedures. It's not as robust as the prior method, but it's historically important. We calculate it by software programs. We can do it by hand with small samples, which is what we'll be doing. So for pooled variance procedures, we start by calculating the pool estimates of variance. Remember, we have s squared, so if we were to take the square root of this, we get our standard deviation. Before you take the square root, s squared will be our variance. So our variance pooled equals our degrees of freedom from group 1 multiplied by our variance squared of group 1 plus degrees of freedom 2, variance of group 2 divided by our degrees of freedom 1 plus degrees of freedom 2, where our variance, or s squared I, is the variance in group I, and you have your degrees of freedom, which is equal by your ni minus 1. So your pooled variance is used to calculate the standard error estimate, which is very similar to what we've seen before. So our standard error of x bar 1 minus x bar 2 is going to equal your variance pooled multiplied by your 1 over your n from the first group plus 1 over n from the second group. Confidence interval calculated virtually the same way, and your t-statistic is set up the same way, with all df's equaling df plus 1 plus dfs plus 2. So everything here you've seen before. So when we have our pooled variance or our t confidence intervals for the same thing we are calculating, there's the data for group 1 and group 2. We have our standard deviation, x bar. When we plug in all the information from the formulas just provided, we get our standard error of 13.56, degrees of freedom. Pooled is 38 for a 95% confidence interval. When we put this in and multiply it out and add, subtract, we get 7.36 to 62.14. It's very similar to what we had before, but it's a little bit different because we're using a little bit different procedures. But all the math here is very similar to what we've been doing. The only thing that is truly different is when we're looking up a pooled t-value for the confidence interval. Remember, it's going to be our t, so we're looking at 38 degrees freedom. Before we were looking at smaller degrees of freedom, so now we're looking at different degrees of freedom, which as the degrees of freedom increase, we're getting closer to that kind of 1.96, and that makes sense to have 2.02. As the degrees of freedom increases, we should be getting closer to that value. So we can do a pooled variance t-test. We already did this on the previous slide, and we get the t-stat of 2.56 with degrees of freedom equaling 38, and you get a p-value of 0.015. So that's for a pooled variance t-test, very similar to what we're doing. Once again, I was going to show you this in Excel, so we'll pull up the Excel spreadsheet again. So the way we do for equal variance, because that's what we were just doing, go to your data analysis tab here, and we just go to our t-test 2 sample assuming equal variances. Now in the SPSS it does both of these. For Excel you can only run one at a time, and right now we're just doing equal variances, so I'll show you that. So you go to your equal variances, hit OK. We have our variable 1 selected and our variable 2 range selected, and our output range is going to be H4. We're going to change that just so I can show you, because that's where that other one was. We're going to move it down here to H23. You just hit OK, and here you go. 2 sample assuming equal variances. Once again, we've got our t-stat of 2.56, which is the same we had as up here, but our p-value is going to be a little less because remember we're using pooled samples for our degrees of freedom. So with this in our two-tailed, we had a p-value of 0.015, 1.4, which is what we got earlier, and this is showing the same thing. So, but they use SPSS, and here I'm showing you how to use Excel to get the same information. Heading back. So part 5 is conditions for inference. So the conditions required for procedures. We want validity conditions. We always want to have good information. You don't want information bias. You don't want a good sample, no selection bias, and no confounding. You don't want anything in there that's leading to getting great results. Basically, you don't want any other types of bias in there. Sampling conditions, you need to make sure they're independent variables that you're sampling, and you want a normal sampling distribution, right? Because if it's not normal sampling distribution, then we won't be using t-tests. We'll be using different statistical techniques, which then become a little bit harder to, make comparisons back to a population doing parametric testing, but nonetheless, you can still do something. It's just not what we're going to be covering right now. So you want to make sure the sampling conditions you always want to get are from normal sampling distributions. So this information here is good to know. We will be doing this in a very small setting, but none of the math here is anything that you haven't seen before, and you get to see a little bit of how it was done using Microsoft Excel. That's all I have for this video, and I'll see you all for Chapter 13 when we start talking about ANOVAs.